I have a circuit today called the justifier. It takes I2S data and it moves the clock, the word clock, an arbitrary number of cycles of the bit clock late in time in order to align it with the data. Now this probably sounds like Greek, but the point is that most digital analog converters you're going to use that have serial input, they accept the data after the last bit, the word clock is latched, and the last however many bits the DAC wants are latched and decoded immediately on the latching of the word clock. So when you look at I2S or even left justify data, which comes out of various types of converters or processors, the data is in the opposite timing. So I'll point at some things here to sort of clarify what I'm talking about here. This upper trace is the word clock. So on the low side, it's one channel stereo audio. Other side is right, left. So it's alternating the channels. And within each channel, there's room for a certain number of bits of audio data. So you can see here there's this is the data trace, the second trace, and it's receiving 16 bits of audio, and then there's some space, and then another 16 bits are sent for the other channel, and this just goes on and on forever. And I should have mentioned that the frequency of this upper wave, this word clock, happens to be the sample frequency that you're listening at. So, you know, say for CDs, it's 44.1 kilohertz, could be 48, 96, 192, whatever. So at any rate, as we see, this window of time for the data to arrive for a given channel has the data positioned towards its beginning at the left. And if you look really closely here, I'll stretch this back out. You can see that there's a gap of 1 bit before the data actually begins. Now this is just a part of the I2S standard. Inter-chip sound is what that stands for. It was developed in the 80s. It's leaving time for the registers and the various devices to clear themselves before the incoming data word. So there's a 1 bit gap there. And then the data begins, and then it ends, and then we carry on to later. So my problem is, you know, my DAC wants to have the data sitting over on the other end of this clock cycle, so that when the clock transitions to the next channel, the DAC can latch the data. Otherwise, its shift register has no idea which bits were which. It's just reading whatever's coming in. And it, say it's a 16-bit DAC, well, it just latches whatever the last 16 bits were that happen to come in. It could be whatever. So we need this word clock to switch, not before, but immediately after the last bit of data, so that the shift register latches it. So what my circuit is doing here, you see this third trace you've probably been wondering about, is actually a copy of the word clock, but it's delayed in time. And so you can see that here, you know, the word clock shifts down, and then so many cycles later, my delayed word clock shifts down, and it copies the original word clock on and on through time. And so if you look closely, you can see that it happens to line up with the last bit of audio from this word of data. And it's telling my shift register in my DAC, my digital to analog converter, to latch whatever the last 16 bits of, it's a 16-bit register, so it latches whatever those 16 bits were. Now, let's say I had a 20-bit DAC. Well, I need this delayed word clock to be shifted over a little more, or maybe it was a 5-bit DAC or something funny, it would be a little earlier. So in my tests and my measurements, I needed a circuit that would give me this delayed word clock, but I wanted it to be variable so I could test different pieces of equipment I'm designing with different resolutions of converters. So what I've done is made a whole mess here. There's a series of counters, shift register, some flip-flops and other logic. So everything on this board is sitting here to do the actual timing. And this board back here is just so that I can format the output of a rotary encoder to adjust the counters which are holding the value that I want to count as my delay. So this whole thing is actually looking at the what's known as the bit clock of my I2S data stream. So the bit clock has one cycle for every bit of room that you could have a bit for. So that works out as the number of bits multiplied by the number of samples per second multiplied by the number of channels. Now there's a catch here. That's the number of bits that would actually fit in a whole frame of the word clock, not the number of bits that are actually put in there, even if they don't use it all up. So we've got to be careful when we do the calculation to remember that it's however many bits of room there are multiplied by the number of channels and the frequency of that word clock. That's what gives you the frequency of the actual data clock or the bit clock, which is chugging along at usually 5 or 6 megahertz depending on the system. So going back here, yeah, this thing is just synchronized. The whole works is synchronized to that bit clock, and by rotating this dial, I am changing the value in an up-down 16-bit counter. I can go either way. And then on every cycle of the word clock, another counter, sorry, this is an 8-bit counter, not 16 bits. On every cycle of the word clock, another 8-bit counter loads the value from this counter that I can, my user configurable counter, and starts counting down until it overflows, carries. Sorry, I should say that it's counting up. You cannot get a carry by counting down. At any rate, it counts up until it's full, and then resets a flip-flop which conveys the state of the word clock to the shift register. So that probably sounds like a bunch of gibberish, but the point is that I can variably control the amount of delay in this lower trace, if my thing will focus, relative to the upper trace. You can see I got no data. My music stopped playing. I'll just restart that. Okay, so the music's going again. You can see there's some data in there. So I'm going to show you what happens when I change the amount of delay that this does. You can see I've actually put this shows in hexadecimal the value that's going into the counter on every cycle that it has to count up from to reach full. Full is FF, which in hex is 8 bits, all ones, all high. So it's going to go from EF all the way up to FF each count. So I can move this along, and you might hear the music in the background go funny. And it just goes to mess. And I go the other way. Yeah, that's what happens when digital circuits decoding properly. If we look at what's happening on the scope, I'm going to sweep along. See, I can go all the way. I like it. And of course, it only sounds best in the right spot. You probably notice, if you can hear it, that it still sounded okay, shifted off a bit. It so happens that the way my stream is received from my USB converter, that there's an extra bit. I won't even get into that, but the point is it shouldn't actually sound proper when it's shifted over, but it happens to the way the stream is formatted. So yeah, that's the circuit I call the justifier. It adjusts the justification of the data relative to the clock. Now purists will probably be saying, hey, well, why don't you shift the data over? That's the correct way to do it. Of course I could do that. I could put in the shift registers, put the data in there. That's fine. But then I need a variable length shift register depending on the amount of data, the resolution that I need to decode at. This solution allows me to take any shift register or any DAC that is serial and attach it and set the delay and go. The other nice thing about this is that if I have, say, a 16-bit DAC and I want to send streams that are 16, 24, 32 bits, whatever, because I am using this method to delay the clock by the number of bits necessary for the given DAC, it will always truncate the remaining bits correctly if I'm using a higher resolution stream that a DAC supports. So it has a happy accident in that it will always decode the upper 16 bits of any stream, which is the correct way to do it. So for any DAC I'm using, if it has equal or greater number of bits, it will always truncate properly. If I have less bits, then as long as they're, well, again, that creates another separate problem, but it's not something you're liable to really care about or run into. So at any rate, the only other thing to notice here is, just as a side note, separate project, here's an 11-bit multiplying DAC out of a radar display unit from the early 70s. So they were generating vector graphics with a pair of these 11-bit DACs driving a vector display CRT out of a completely digital state machine, which was developing all of the numbering and lettering and the maps and so on the display. So yeah, I got this as surplus, and I've been hanging on to it for however many years and didn't know if it worked. I've got a bunch of them. They go in a puck, should be in there, but I took it out so I could look at it and hook it up. And I thought, well, what better thing to do than to try and see if it does okay at audio. And yeah, it's only 11 bits resolution, so there's a lot of signal correlated noise down at the bottom of the dynamic range. But outside of that, it sounds astonishingly good. It has very, very decent distortion characteristics, and this is operating with no reconstruction filter, no deglitcher. So it would even be a little better with those things included. But yeah, I thought, what better to try this circuit on than with some really arcane, oddball, high-end thing from who knows when. So that pretty much covers it. Sorry for the extremely wordy description. I hope it was possible to follow. You probably get the gist of it, though, just seeing the relative timing. I'll put my hand... Oh, the camera's really not the wide angle. There it is again. You can see the effect. All right, that's enough of that.